Welcome. So we are going to start our last module on some special topics that are very, very important, especially when it comes for optimization of deep learning models. And the first topic that we're going to talk about is basically the concept of second-order guarantees. So the idea is that so far, when we were talking about the guarantee on the training error, when using training algorithms such as SGD and its variations, we basically talk about the number of iterations it takes to reduce the norm of the gradient, right? Now, that is in some sense a weak guarantee that requires very mild assumptions to establish. In this lecture, we're going to basically see what we can do in terms of establishing a stronger guarantees. In particular, second-order guarantees, which basically means points that have potentially higher quality, as opposed to just points that have a low gradient norm. Okay, so that's basically what we're going to talk about. So what was our setup? So we typically were interested in minimizing the average loss over the entire training data. So in particular, this is the empirical loss that we are interested in. And we established quite a few number of results, in particular for our favorite method, stochastic gradient descent, which follows this very simple update, goes from the current update to the next one by following the negative direction of a stochastic gradient. We show that it satisfies this bound. In particular, the expected gradient norm is less than epsilon if you run the method with this many number of iterations. Okay. Now this is called the first-order solution, as we discussed before, because we are only assessing the quality of the solution in terms of its gradient norm. Okay. And in principle, it can be a local minimum, a local maximum, or a saddle point. Okay. Obviously, we are interested in situations where we have a local minimum, which basically means that at least locally it's a good solution. Okay, local maximum is highly undesirable because we are interested in minimizing the loss, right? So local maximum is it locally maximizes the function, complete opposite of what we had in mind. And saddle points are also not very interesting for us either, because that means that locally we are not necessarily minimizing the function. So we could potentially do better than that. Okay, so all of these are points at which the gradient norm is small. That's why we are looking for a stronger guarantees in order to distinguish these two and hopefully only talk about methods that converge to local minimum. Okay. All right, so let's go over a few examples to basically see what scenarios where points at which the gradient is 0 could be a local minimum, local maximum, or a saddle point. Okay, so in particular, let's first consider this cubic function. So if you were to plot this function, it would look like following. So something like this. So naturally, there is a local maximum, and there is a local minimum, right? So these are points at which the tangent is basically completely perpendicular, right? So therefore the gradient is 0. Okay. So let's find the derivative in this case. Okay. So the derivative of the function will be basically w squared minus 1. So if we set it equal to 0, then we find that we have two solutions. Let's call them w hat, which are plus and minus 1. Both of these are first-order stationary points at which the gradient is 0, but one of them is a good solution, it's a local minimum, the other point is a bad solution, is a local maximum. How can we detect or identify which one is a good solution, which one is a bad solution? Well, we have to look at the curvature of the function, in particular the second-order derivative. Because that could determine the curvature. In particular, if the curvature is positive and the function is curving upward, we can consider that point to be a local minimum. On the other hand, when the curvature is negative, so the function is locally concave and it's curving downward, then that point is a local maximum. Okay, So if I were to calculate the curvature, then the second order derivative, in this case that would be 2w. And from this we can see that w hat is equal to 1 is basically a local minimum, because in this case the curvature will be positive. Okay, so because curvature is positive. On the other hand, w equal to -1 is local maximum. Okay, so in this case the curvature is negative. Right, so therefore, although both w equal to 1 and +1 have a zero gradient, so first order is stationary, one of them is good, the other one is bad, right? So in particular, we're going to call this one a second order solution, because not only the gradient is zero, but also the second order derivative is nice and positive. On the other hand, the other solution is not, right? So that's why if we can talk about second order stationary points, this is basically what we're going to talk about, and come up with algorithms that can guarantee finding second order solutions, we can therefore exclude all of these bad local maxima, right? So we can say that our solution is gonna be something nice and useful, okay? All right, so let's talk about another example. So it's another cubic function. So if you were to plot it, it's going to look something like this. Okay. So what are the derivatives and the second order derivatives? The derivative is basically just w squared. Okay. So if I set, therefore, this to be 0, I find that w hat will be 0. So I have one stationary, first order stationary solution, and that's basically the origin. Okay. Now, is it a good solution? Is it a bad solution? Well, we have to look at the second order derivative. So the second order derivative will be w, 2 times w. And again, here, the second order derivative of w hat is also equal to 0. So therefore, by just looking at the second order derivative, I cannot determine whether this point is a local minimum or a local maximum. Okay. In particular, this is a saddle point. Okay, so this is a higher order saddle point, the point at which the gradient is 0. The second order derivative is also 0. That's why we cannot determine whether it's again local minimum, local maximum, or a saddle point. Right? So it's a higher order saddle point, which is also not desirable. Okay. All right, so therefore this is another example where we have a first order stationary point, but that's neither a local minimum nor a local maximum, as opposed to the previous example. However, it is a saddle point. Okay, so let's talk about another example. So here, if you were to plot it, it's gonna look something like this. Okay, so again, first order derivative is just w cubed. So our first order solution is again w hat equal to 0. Second order derivative will be 3w squared. So it means that the second order derivative is again 0. So by looking at these two, we cannot make a determination. But in this case, it turns out that we actually have a global minimum. Okay. So this is a global minimum for us. So it is a good solution. Okay. All right. So and finally, let's consider this other example. So if I were to plot this, it's going to look something like this. Okay. So I have two global minima, one here and one here, and then I have a local maximum. Okay. So if I were to calculate the derivative, so the derivative would be basically 2w times w squared minus 1. So if I set it equal to 0, therefore, I find that w hat, my first order solutions are basically 0, 1, and -1. So one of them is a local maximum, very bad solution. Two of them, on the other hand, are global minima, so a good solution. So how can I make a determination? Again, I can calculate the second order derivative. Okay. So if I calculate the second order derivative, this will be something like W 2 times W squared minus 1 plus 4W squared. Okay. So if you plug in, for instance, W hat equal to 0, you'd see that the second order derivative is negative. So we can make a determination that that is a local maximum. So it's not a good solution. On the other hand, when I plug in 1 or minus 1, I'll see that the second order derivative will be positive, strictly positive. So for this two, the second order derivative will be positive. For this guy, the second order derivative will be negative. So therefore, in this example, by looking at the second order derivative, second order information, I'll be able to make a determination that which of my first order station points are good and which one are bad. Okay. All right. So all of these examples were in first or like in one dimension. And basically what we were trying to do was to identify the first order solutions and see whether by looking at the second order information, second order derivative, we can determine which solution is good, which solution is bad. In some cases we could make that determination, and in some cases we could not. Okay. Now let's also see an example in 2 dimensions. And based on all this, we're going to formally define our notion of second order stationarity. Okay. So let's consider this function, which is called basically like a saddle point. So this is basically where the saddle comes from, because it looks like a saddle that you use to, let's say, ride a horse. Okay. Now in this case, origin can be shown to be a first order solution, because if you just calculate the gradient, so it will be something like 2x 2y. So if I set it equal to 0, therefore I can find that origin is a first order solution. Okay. Now, is it a good solution or a bad solution? Well, for that I have to look at the second order information. In multiple dimensions, that's basically the Hessian. So we have to calculate the Hessian, and that basically will be 2. Sorry, there is a minus here. It will be 2, 0, 0, minus 2. Okay. Now, previously we said that, if I want to see if a point is a local maximum or a local minimum, I look at the second order derivative. If that's positive, then that's basically a local minimum. If that's negative, that's a local maximum. In multiple dimensions, we have to look at the eigenvalues of Hessian. Okay, so if all eigenvalues are positive, then that point will be a local minima. If all eigenvalues are negative, that point will be a local maximum. And if it's in between, then that point is a saddle point. In this case, we have 2 eigenvalues, because the Hessian ends up being a diagonal matrix, and you may know from your linear algebra courses that the eigenvalues of the diagonal matrices are basically the entries on the diagonal. So I have 2 eigenvalues. So lambda 1 is equal to 2, and lambda 2 is equal to minus 2. One of them is positive, the other one is negative. Okay, so that basically means that there is a direction of increase, okay, of the function. So this is basically the direction of increase associated with the eigenvalue lambda equal to, so these are associated with lambda equal to 2, direction of increase. On the other hand, I have a negative eigenvalue, so I have directions of decrease. So these are basically associated with lambda equal to minus 2. Okay. So therefore, locally, some directions are increasing the function value, some are decreasing. That's why I'm going to have a saddle point. If all eigenvalues were positive, then by deviating slightly from this point, I would be increasing the function value. So therefore, that would be a local minimum. If all eigenvalues were negative, by deviating slightly, I would minimize, I would reduce the function value. So that could mean that, therefore, the point is a local maximum. Okay. All right. So based on this, therefore, we can define our notion of second order stationarity. Basically, now we have a way to talk about what we need from the second order information in order to basically distinguish between local minima, local maxima, and saddle points. Okay, so that gives rise to this definition of approximate second order stationarity. In particular, we call a point epsilon 1, epsilon 2 accurate second order stationary if it satisfies two conditions. First of all, it has to be first order stationary point. So it means that the norm of the gradient has to be less than some epsilon, okay? Epsilon 1 in this case. Also, we impose the condition that the minimum eigenvalue of the Hessian is not too negative, okay? So, so basically we say that the minimum eigenvalue is at most minus epsilon square, where we, epsilon 2. Where epsilon 2 is basically a very small number, okay? So if a point satisfies these two conditions, we would say that this is a basically a second order stationary point, okay? So this example that we just went over does not satisfy this condition. It satisfies the first one because the gradient is exactly 0. But when I look at the eigenvalues, the minimum eigenvalue is minus 2. So minus 2 is not a small number. So there are many epsilon 2s for which minus 2 is actually more negative. So basically, this point won't be a second order stationary point. Okay. So therefore, this is the definition that that we're going to work with to sort of find solutions. So when we say a second order solution, this is exactly what we mean by that. A point at which the gradient is small. Also, the minimum eigenvalue of the Hessian is not too negative. All right. So, what is what does this definition mean? Okay. So, in terms of the examples that we saw before. Okay. So, in particular, this definition is useful because it excludes two bad first order solutions. First of all, it excludes local maximum because local maxima are points at which the eigenvalues are very negative. All of them are negative. So they violate the second requirement. So by this definition, we are excluding them. Also, we are excluding simple or strict saddle points, like the previous like the examples in the previous slide. Okay. So intuitively, these are saddle points that we can detect them by simply looking at the Hessian, second order information. Okay. On the other hand, there are some saddle points that are more complicated. There are higher order saddle points, which basically means that we cannot detect them simply by looking at the Hessian. In particular, the Hessian is like 0 at those points, like the example we saw earlier, like the simple cubic function. Origin at this point is basically a higher order saddle point. We cannot detect that by just looking at the Hessian. Okay. So therefore, this definition is excluding local maximum and simple saddle points. It does not, however, exclude higher order saddle points. Okay. So two examples of higher order saddle points are the ones that I'm demonstrating here. For instance, this function in 2 dimensions is going to have a higher order saddle point at origin. So we cannot detect that by just looking at the Hessian. So this point is going to be a point that satisfies the second order stationarity condition we just defined. Okay. Also, another famous example is basically the monkey saddle point. Okay. So it's given by this function. So origin in this case is again a higher order saddle, which again the gradient is 0. The second order, the minimum eigenvalue of the Hessian is also not too negative. So it satisfies the condition we imposed. However, it's not a local minimum. Okay. And just a side note, this is called the monkey saddle because monkeys have tails. So there are 3 directions of decrease here, as opposed to 2 directions for the regular saddle. Okay. All right. So okay. So therefore, this definition is useful because we are excluding at least local maxima and simple saddle points. but the solution still could be a saddle point, which remains to be undetectable by just looking at the Hessian. Okay. Nonetheless, we can argue that it is a good definition, okay, so to work with, because in many problems we actually are going to have only local/global minima as well as simple saddle points. So it is very unlikely to let's say see higher order saddle points. So therefore, if I have an algorithm that can find a second order stationary point, that solution is going to be a good solution. It's going to be a local minimum or a global minimum. Okay. So one example of this kind of problem is the matrix factorization problem, where the idea is that you have a matrix and you want to factorize it into two factors, P and Q, as I'm demonstrating here. So you have a low rank matrix, and you assume that therefore that means that it can be factorized as a product of two other matrices, let's say P and Q transpose. And this is a problem which is a non-convex problem. And there are many, many solutions. Okay, so to see that, consider this scenario. Let's say that I gave you an optimal solution P star and Q star. Okay. Now, if I permute, let's say, two columns in P, and also permute the corresponding columns in Q, the product won't change. Okay, so that means that any permutation that maintains this ordering is also going to be an optimal solution. How many of these permutations do I have? An exponential number of them, a combinatorial number of them. So therefore, there are many, many global minima for this problem. Okay. And it turns out that a similar idea also applies to deep learning models. So we can kind of think of deep learning models as like more complicated matrix factorization problems, matrix factorization models, such that if I, let's say, permute columns of weight matrices in my deep learning model, such that I maintain the ordering, I will still get the same optimal model. So it means that the number of optimal solutions is, again, an exponential number. Okay. Now, we have a lot of these global minima, and it turns out that these global minima are basically separated by simple saddle points. So the kind of solutions that I have are basically simple saddles as well as global minima. So if I give you an algorithm that can avoid these simple saddles and find a second order solution, therefore it is guaranteed to find the global solution. Okay. All right, so here I've tried to sort of visualize this idea, right? So, and what we have done basically, we have this simple one-dimensional function, which kind of resembles the matrix factorization problem. It's as if we are trying to factorize 1 into 2 factors, x and x. Okay, so this is the most simple case for matrix factorization. And from this, now we want to go to higher dimensions. So in particular, I'm going to basically construct this other function. So you can think of it as basically a kind of a simple matrix factorization problem in 2 dimensions, basically. Okay. Now I've sort of depicted this function here. Okay, and it turns out that this function has 4 global minima and 4 simple saddle points. So this is one solution, another one, and another one here. And they are separated by simple saddle points. So there is a simple saddle point here, another one here, and one here. Okay. And if we continue this process, we're going to basically generate an exponential number of global minima and global and simple saddle points. Okay. So in particular, if I go into 3 dimensions, then I'm going to have 8 global minima separated by 8 simple saddle points. Okay. So therefore, for these kind of problems, which again have some connection to deep learning optimization problems, it is just sufficient to avoid these saddle points, right? So it is sufficient to find a second order solution, because that would imply that the solution is going to be a good solution. It's going to be a local minimum. All right. So how can we calculate the second order solutions? How can we find them? In particular, what kind of algorithms we need. Okay. So to answer this question, let's first go back and look at what we needed when we talk about first order solutions. Okay. So we required accessing the gradient, for instance, in the case of gradient descent, or a good approximation of the gradient, for instance, in the case of a stochastic gradient descent. So that's what we needed. We impose a smoothness of the function, which basically meant that the gradient is Lipschitz. And note that gradient is a first order quantity. So basically, what this means is that when we were interested in first order solution, we impose requirements on first order information. Okay, so we required a good access to gradient, and also we require that the gradient is well conditioned, meaning that it is Lipschitz. So therefore, intuitively, we might expect that we also need some requirement on the second order information, namely Hessian, if we are interested in second order solutions. Okay, so in particular, we may require accessing the Hessian or a good approximation of that, or we may impose second order smoothness, which basically means that not just the function is smooth, but the gradient of the function is smooth, or equivalently, the Hessian is well conditioned and Lipschitz, because Hessian is the second order information, second order quantity, as opposed to gradient, which is first order quantity. Okay. All right. So this is basically an intuitive expectation, and as we're going to talk about in the next part of the video, this lecture, we will indeed require that the Hessian is well conditioned and it is Lipschitz. However, we're going to discuss two methods, two very elegant ideas in the literature. One of them requires accessing the Hessian, or in practice, a good approximation of the Hessian. The other one only requires basically gradient information, first order information. Okay. So the main idea behind these two methods, as we're going to discuss, is as follows. So the first method that utilizes the Hessian information is going to leverage that information, as we saw in these examples, to detect saddle points and avoid them. Okay. Second kind of methods, on the other hand, is going to intentionally inject noise into the optimization process to avoid saddle points, avoid simple saddle points. And the main idea here is that saddle points, as opposed to local minima, are unstable. So if I slightly perturb my solution, I might be able to find a direction to decrease the function value. So we're going to leverage this idea into our algorithm design. Okay. All right. And the last point, as I mentioned here, so I'm going to mention avoiding saddle points or escaping saddle points. And that basically means that we want to find a direction at or near a saddle point to decrease the function value. So that means that we are literally escaping the saddle points and finding our way towards a local solution. So as I mentioned then, we're going to talk about these kind of ideas in the next part of this lecture. I'll see you there.